Welcome back. So now we're going to talk about section 12.3, which is on relationships between shapes. So this is the second level in the development of understanding different geometric concepts. And so remember, so we kind of introduced this level last time. So remember at level 0, the idea is that we can holistically identify, or a child can holistically identify certain shapes, but not always super accurately. At level 1, a child starts to identify different components of a shape and different properties that they might have. At level 2, the student is able to take those different components and use those to form relationships between different types of shapes. So that's what we're going to talk about here in this section. And so it's kind of a short section. I just want to break down the kind of different ideas. And so we're going to first start just talking about triangles in a little bit more detail. And basically, there are two different ways we can classify the type of a triangle we're talking about. We can classify it by looking at its angle, or we can classify it by its sides. And if we classify by looking at angles, we might be able to see whether or not there are certain triangles that could be both right triangles and isosceles triangles. So remember, a right triangle is a triangle that has one right angle in it, or a 90-degree angle. An isosceles triangle, I think when we defined the isosceles triangle, we said 2 of the sides were the same length. And in order for 2 of the sides to be the same length, it also means that 2 of the angles have to be the same length. Okay, so there's a question, the started question from last time kind of alludes to the fact that there are different ways to define these geometric figures besides how we defined them last time, or how we characterized them last time. And sometimes we can characterize them based off of the side length, and there might be a similar or equivalent characterization based on the angle. So for isosceles triangles, we could equivalently say they have 2 angles that are the same size. And so it is possible for a triangle to be both a right triangle and an isosceles triangle. So in this intersection of this Venn diagram in the middle here, these are 2 triangles that fit both. Okay. So notice though that the angle that is the same can't be the 90-degree angle, right? Because then the triangle would have, those 2 angles would add to 180, and the triangle all the angles of a triangle should add to 180 degrees. We'll actually talk about this more, I think, in the next section. Okay, great. So we can also classify triangles by their side length, which when we defined isosceles triangle, that's what we did. And so here we can think of this diagram represents, here we're talking about all the triangles, and we can talk about a triangle is either going to be scalene, in which all sides are different lengths, or it's going to be isosceles for any given triangle. So it falls into one of these 2 groups. If it's isosceles, it means 2 of the side lengths are the same. It could actually still be equilateral, meaning that the 3rd side length is the same. Just because we have an equilateral, so if we have an equilateral triangle, it will be isosceles. But just because we have an isosceles triangle doesn't mean it will be equilateral. So kind of abstracting away from the particular examples and recognizing these relationships between different types of triangles is kind of something that happens at this second stage. Okay, and if you're forgetting what any of these definitions are, refer back to the previous section where we have defined the scalene, isosceles, and equilateral triangles, and the right triangles. Okay, we can do a similar thing with quadrilaterals. And I think we have, so if we have a quadrilateral, that just means a four-sided figure. It says nothing about angles or lengths of sides. So there are three options. If I have a quadrilateral, something with four sides, it could be a trapezoid, it could be a parallelogram, or it could be what we call a kite. And so we haven't really talked about trapezoids or kites yet. And so I'll refer us to this description of a kite before we go back and go back to that chart in a second. So we've talked about parallelograms. They are four-sided figures with two sets of parallel sides last time, but your book also provides a nice like definitions of a kite and a trapezoid, and they do so in the same way they did for the definitions in the last chapter. So they give a nice model and a as well as the name and description. Okay, so for a kite, the obvious model is an actual kite. So that's a good model to think of when you're thinking about describing these things. So we might be able to, at level 0, just saying the word kite, you could, at level 0, kind of visualize what a kite would be. But now we want to be able to give a description in words and kind of have an idea of exactly what is a kite and what is not. And a kite is a quadrilateral with two non-overlapping pairs of adjacent sides that are the same length. So, the takeaway on this definition, or the key part of the definition here, is that there are two pairs of sides that are the same length, but they're the ones that are next to each other, as opposed to the ones that are opposite of each other, like they would be in the parallelogram. So here, both these sides are the same length, and both of these sides are the same length, and that's what makes this thing a kite. Okay, with a trapezoid, they use the model of a bike frame. It's not the best image, I think, for this example, just because it's hard to see that this actually is a trapezoid and not a triangle. But it's hard to find trapezoids in real life, so it works. Okay, so this is our model for a trapezoid, and it's a quadrilateral with exactly one pair of parallel sides. So what that means is a trapezoid cannot be a parallelogram, right? Because a parallelogram has two pairs of parallel sides, and a quadrilateral has to have exactly one, not just one or at least one, but exactly one. And so here we can see these two parts of the bike frame are parallel, but the other parts are not parallel. And so these two not being parallel is just as important in the definition of a trapezoid. And an isosceles trapezoid, they have modeled with a silhouette of a drinking glass. And it's a quadrilateral with exactly one pair of parallel sides, and the remaining sides are the same length. We have one pair of parallel sides. Here it's the top and the bottom of my drinking glass, and the remaining sides are the same length. Okay, so that is an isosceles trapezoid. So going back to our chart up here, we have, if we're talking about a quadrilateral, it has to have four sides. It could have all four sides being parallel, and that's obviously a parallelogram. It could have exactly one pair of sides being parallel, and that's a trapezoid. Or it could have no sides being parallel, and that's a kite. Okay, and so those are our three options when we're talking about a quadrilateral. if we have a trapezoid where two of our sides are parallel, or exactly, yeah, two of our sides are parallel, then it could possibly be an isosceles trapezoid if it also meets the fact that the remaining sides are the same length, but not all. So all isosceles trapezoids are obviously going to be trapezoids. That's kind of obvious from the name, but not all trapezoids are isosceles trapezoids. So if we have a parallelogram, we could say that it has four right angles, and so it's a rectangle. Or we could say that all of its sides have to be the same length, right? So one characterization is kind of based off of the angles, and a different way of characterizing is based off of the sides. Where these two things overlap is with a square, right? So saying something that has all the same sides lengths doesn't mean necessarily all of its angles are right, but if they are, it's square. And saying something has all right angles doesn't mean it's all of its side lengths are the same, but if they are, it's a square, okay? Great, and based off this diagram too, I should point out, kites, the set of kites and parallelograms aren't exactly disjoint, because it falls under that a rhombus is definitely a parallelogram. We've talked about that before, but a rhombus is also a kite. So because they have two non-overlapping pairs of adjacent sides that are the same length, because all of their sides are the same length. Since all their sides are the same length, both pairs of sides are the same length. So all rhombi are kites as well as parallelograms. So we have in this intersection of kites and parallelograms, we have rhombi. Okay, great. So I want to finish off this section with a couple examples just to kind of help get you through what the homework looks like. So I think these Venn diagrams are really helpful for understanding the relationships between these figures. It might be helpful for you to take these charts or these kind of diagrams that they've drawn here and turn them into Venn diagrams, if that makes more sense to you. So that's kind of part of what they're doing here for question number 4 here. So we have a set of these 3 types of Venn diagrams, and we want to know which of the following pictures. So in part A, we want to know which of the following pictures of sets best represents the relationship between an isosceles triangle and a scalene triangle. So remember, in scalene triangles, none of the side lengths should be the same. And in isosceles triangles, 2 of the side lengths should be the same. And so this is got to be diagram 1. There's no overlapping cases. And then the next part, B, asks which represents the relationship between isosceles triangles and equilateral triangles. Isosceles says 2 of the side lengths need to be the same. And if and equilateral triangles, 3 of the side lengths are the same. So if something has 3 side lengths the same, then it has 2 side lengths the same. So this is an example of something that fits into the third case. So where the equilateral triangles would make up this smaller circle that fits inside the isosceles triangles. Part C asks which represent the relationship between isosceles triangles and right triangles. Here is an example where I think this looks like 2. There are some right triangles that are also isosceles. I think we saw this diagram previously. And there are some isosceles triangles that are right. So actually, this is exactly this picture. Here you go. Here's exactly how you would illustrate it. Right? And finally, part D asks which represents the relationship between equilateral and right triangles. This one's a little bit trickier. So equilateral triangles have 3 side lengths the same. And so that also means we'll have to use a little bit of deductive reasoning here. And that also means that all of their angles have to be the same length, right? And since the sum of the triangle's angles has to be 180, it means each of the angles must be 60 degrees. And so it can't have any 90-degree angles or right angles. And so again, this set should be disjoint. Or these two sets should be disjoint. And this should look like the first image. Okay, so wanted to move on to another question. I mainly wanted to look at this one because there is a problem in your homework referring to pentaminos. And so I just wanted to talk about them briefly so that you could complete that problem. And the main thing I wanted to mention, so here's your definition of a pentamino. This is in, I think, part A, number 8 of 12.3. So a pentamino is made of 5 connected squares that touch only on one complete side. So here's an example of something that is a pentamino. We are touching on one complete side, but here's something that's not. They're touching, but not on a complete side. And 2 pentaminos are the same if they can be matched by turning or flipping, as shown. So I think, so these 2 pentaminos are the same one because I can flip this guy and get this guy, or vice versa. Okay, so they say the initial problem in chapter 8, so at the very beginning of chapter 8, you should have found that there are 12 different pentamino shapes. So I just wanted to refer you to the answer is actually on page 333. They ask you to find all of the different pentaminos, and that's on page 333. You should see this solution. So mainly I wanted to point that to you to that so that you could answer that homework question without hunting around too much. Okay, and so this question asks us which of the pentaminos have reflection symmetry and indicate the lines of reflection. And then we wanted to ask about the rotation symmetry. So here I'll circle what, so the different pentaminos, this is kind of confusing how they worded the answer, so I also wanted to look at that. So here's a bunch of them. So here's the first 1, 2, 3, 4, 5, 6, 7, 8. So these are with 3 in a row. They broke it down into different cases when they found them. There's that one, and then there's these 2, and this one. So these are the different pentaminos. Okay, so let's see which ones have reflection symmetry. And let's see here. So let's see, I don't think the first one does, but I do think the second one does. It looks like it has one reflection symmetry along this line. The third one, I don't think it does, but it looks like it should. It definitely has a rotation symmetry though. So this has a rotation of a 180 degrees. Should give us symmetry. I should say the first one and the second one don't have any rotation symmetry, it looks like to me. I think this fourth one here has no symmetry. Let's see, this one here has a reflection symmetry, but I don't think it has any rotation symmetry. So let's see, it has a reflection symmetry like that, and I think that's the only one. This guy looks like no symmetries to me. This guy looks like it does. Don't think it has a rotation symmetry, but I think it has a reflection symmetry. Yeah, here. The colors are just to indicate where we're adding. They don't mean anything about the big distinct pentaminos. So I think it has a reflection symmetry across that line. But yeah, I don't think any rotation. This one has all sorts of stuff, right? So it looks like it has 3 different rotations that are the whole 360 degrees. So it looks like there's 1 by 90, 1 by 180, and then 270. And then it also has all sorts of reflection symmetries. So we can reflect across this line and across this line and across the diagonals. So it looks like to me it has 4 different reflection symmetries and 3 different rotation symmetries. All right, just a couple more cases to go. This guy here has a reflection symmetry across this horizontal line and one across the vertical line. And it has a rotational symmetry of 180 degrees. This guy doesn't appear to have any symmetries to me, nor does this one. But I think this last one has at least one reflection. Let's see, we can reflect across this line. And I think that might be all we have. Don't think there's any rotations in there. Great. So that kind of answers A and B together quickly. So again, if you are looking for this, all these, the pictures of the different cases of pentaminos, this is on page 333. Last but not least, I just wanted to point out a couple of starred problems for you to answer for participation if you would like. These are on page 588 of your book. So number 10 and number 11 are the ones that I would, are the ones that I point out right now. Number 10 is a really famous problem about, it's kind of got a practical application about crossing water and gas lines, but it's a famous problem of graph theory. And then number 11 is, again, kind of alludes to what I mentioned earlier, which is there are different formulations of definitions for like a rectangle or a kite or a rhombus that might be equivalent to the ones that we gave before. And so we want to determine on number 11 if these 3 characterizations could also be definitions of a rectangle, kite, or rhombus. Okay, that's all. I'll see you next time.